In this video, assembly is used to program ATmega328 EEPROM, where data are written and read from the 1 kilobyte EEPROM. The main application of EEPROM inside a microcontroller is to store non-volatile data that can be used by a running code. Within the ATmega328 found in the Uno and the Nano, there is a 1 kilobyte EEPROM, and in the ATmega2560 found in the Mega, there is a 4 kilobytes of EEPROM. In this video, we'll focus on the EEPROM found within the ATmega328, and the memory organization is shown here, which is made of 1024 memory locations, and each location has a 16-bit address, and each memory location can store a byte value. There are 4 registers associated with the EEPROM. We have the EEPROM address register low and address register high. These 2 registers are used to store the 16-bit memory address of the EEPROM memory location. We also have the EEPROM data register, which acts as a buffer between the CPU and the EEPROM. So if we want to write a byte to a memory location, the EEPROM, first we need to write it into the data register, and then from the data register it is copied onto the memory location. And vice versa, if we want to read a byte from a memory location in the EEPROM, it is first transferred into the data register, and then we read it from the data register and pass it to the CPU. Next we have the EEPROM control register, which determines the type of operation, whether a read or a write operation. And within this register there are 4 control bits. We have the EEPROM read enable, which enables the reading from the memory location of the EEPROM. We have the EEPROM write enable, which enables the writing to the location. And we have the EEPROM master write enable, which must be set in order for the write operation to occur. And we have the EEPROM ready interrupt enable, which enables the interrupt capability of the EEPROM. This is a flowchart which shows the write and read process to the EEPROM. Before we can write any byte to a memory location of the EEPROM, we have to make sure that the control bit EEPROM write enable is 0, which means that the EEPROM is ready to receive new data. Once it is 0, then we can write the 16-bit address into the EEPROM address register, and then send the byte to the EEPROM data register, and then we set the EEPROM master write enable, and then we set the EEPROM write enable. To perform the EEPROM read operation, again we need to check the status of the control bit EEPROM write enable. Once it is 0, then we can write the address 16-bit address into the EEPROM address register, and then we set the EEPROM write enable bit, and then we read the data from the EEPROM data register. In this first example, we want to write a byte to EEPROM memory location 005F, and then we want to read the byte from the same location and send it to port D so that it can be displayed on the connected LEDs. For the EEPROM write operation, we first configure port D for output, and then we see whether the EEPROM is ready for the write operation by checking the status of the control bit EE write enable to see if it is 0. And we can do this by using the assembly instruction skip if bit is clear. And once this bit is 0, then we can move to the next instruction. Next we write the 16-bit address 005F to the address register by writing the high byte of the address to EEPROM address register high and the low byte to the low register. Next we write the data byte to the data register, and then we enable the EE master write enable and the EE write enable in order to start the write process. And for the read operation, we once again check the status of control bit EE write enable. Once it is 0, then we can set the EE read enable digit and then read the byte from the data register and then output the byte to port D. Before you upload the sketch to the Arduino Uno, first remove the two LEDs connected to pins RX and TX, since these two pins will be used during the loading process. Once the sketch is successfully loaded, then you can reconnect the LEDs and observe the output on port D. In this next example, we store 14 bytes in EEPROM and then continuously read and display the bytes on LEDs connected to port D. And we get this Knight Rider effect. To get the Knight Rider effect, we need to store these 14 bytes in the EEPROM, starting with byte 1, which is the initial byte, which has this value. We store this in the EEPROM, and then we apply logical shift left by using instruction LSL to the byte, and then we store this in EEPROM, and we continue shifting and storing the bytes until we reach this value here. And then we apply logical shift right by using instruction LSR, and we shift and store until we reach byte 14, and then we have 14 bytes in the EEPROM. And in the read operation, we need to read the 14 bytes continuously to get that effect. A quick look at the assembly code. We first configure port D for output, and then we store the high byte of start address 0 in the EE address register high, and then we define the initial byte to be written to the EEPROM. Next, we wait until the EEPROM is ready. Once it is, then we store the low byte of EEPROM address in the address register low, and then we write the byte to the data register, and then we set the master write enable, and then we set the write enable in order to write the byte to the EEPROM. Next, we increment register R17 so that we point to the next memory address, and then we check whether we have copied all of the bytes to the 14 memory locations. If not, then this instruction will be ignored, and we go to this next instruction, which is have we written to the first 8 memory locations? If not, then this instruction will be ignored, and we go to the next instruction, which is the logical shift to left of the byte. And then we jump to label L1 and we repeat the process. After we copy the first 8 bytes to the EEPROM memory locations, this branch instructions becomes true, and we jump to label shift right, where we will apply the logical shift to right to the byte, and then we jump back and repeat the process. Once all of the 14 bytes have been written to the memory locations, this branch instruction becomes true, and we jump to this label to start the read operation. Before we start the read operation, we once again check the status of the EEPROM to see whether it is ready for an operation. Once it is, then we point to the first memory location and we enable the read operation, and then we get the byte from the data register and store it in register R16, and then we output the byte to port D. After we output the byte to port D, we apply some time delay, and then we increment register R17 to point to the next memory address, and then we check whether we have read all of the 14 bytes from the memory locations. If not, then this instruction will be ignored, and we jump to L2 and we repeat the read process. Finally, when all of the 14 memory locations have been read from, then this instruction becomes true and the branch jumps to exit 2, where we go back to label EX1 and repeat the read process. In conclusion, the internal EEPROM of the ATmega microcontroller can easily be programmed using assembly. And in future videos, more applications will be demonstrated, such as a servo motor controlled by data stored in EEPROM.